Welcome to the second part of our video series where we're looking at a radio frequency amplifier model within classic Icepak. In our previous video, we built all of our components from scratch. Essentially, within our cabinet, we have a fan to cool down the system. We also have a heat sink that sits on top of our heat generating amplifier. Heat sources are defined as 2D sources named device here. We also have a PCB as well. Next step is once the geometry is defined, the components are defined, is meshing. So for meshing, a lot of times, we want to do some assembly strategy, which does two benefits. One is better meshing. You can assign different meshing properties, sizes to different assemblies. The other is a better structure. Right now, all these pieces are individual, as you can see under the tree, but we were going to start building some assemblies, put them into groups together so that it will look better organizationally. Another thing, before we jump into that, I want to do is, about the views. For example, right now, we have some, verbiage on the model, like, if you don't want the part names, component names here, what you can do is go under view. We can do display object names. We can do none. This will never show it, or maybe a better one. I kind of like his object names selected. So whatever selected. So if I select PCB, it's going to show those. Another way, to limit the view, maybe we can do, for example, if you wanted to see certain types of objects, if it's very crowded, I just want to see, fans or heat exchangers, heat sinks, etc. You can turn things off, like, here I kind of made heat sinks invisible, which, removed it from there. We can remove packages, etc. Or let's just, bring those back. So keep that in mind. What I'm going to do is I'm going to organize this using two separate assemblies. So first, what I want to do is do the amplifier part. I'm just going to switch to the positive X view. And then I'm going to put my finger on shift and I'm going to start drawing a box. But as you can see, I did not get it fully on all the devices. So let's give it another try. Let's go here, click shift, and then draw a box. Now what I have are, all the amplifier components. So I'll go to housing, do a right mouse click, and what I would like to do is create an assembly. So once I click this, what you'll see is all these guys kind of vanish because they're all under assembly 1, which contains all the selected objects within that box. So let's go ahead, rename this as our fan assembly. So right now we have two assemblies within our cabinet. So let's start talking more about meshing. One of the concepts is called slack with Icepak meshing. This is essentially a small additional marginal distance from your object, which you specify so that your passage from between non-conformal cells are smoother. So if you have put a very small slack value, that will decrease the number of cells, but then it may be difficult for the mesh to generate a quality one. On the other hand, you don't want too large slack values either, because that will have excessive mesh bleeding. So typically you want to have slack values so that you get 1 to 2 cells across the slack region. In this particular model, we have the two assemblies, and as you can see, the distance between them are pretty high. So you can you can easily do non-zero slack values. So let's go ahead start defining our slack values. So I'm going to double click on Amplifier and select meshing. I'm going to select mesh separately and then define our slack settings for the amplifier. So we can have 0 slack in the X direction. Let's put 20 millimeters and about 10 millimeters. That's minimum. And then let's have maybe, 50 millimeters for our amplifier. So let's hit update and done. Then we can go to fan. Again, same strategy. We go to meshing, mesh separately, and let's put our slack settings. So the slack for our fan can range between these min and max values in their respective directions. Let's hit update and done. Next step, since we defined our assembly related mesh control, we can just go to our general mesh controls. We're going to go to model and then we're going to select generate mesh. Another way to get to this window is we can select this generate mesh button from the top ribbon. Okay, so this is going to bring us this window where now we're going to select our meshing method and then do the generation, and we'll also define some maximum element sizes, gaps, etc. So let's, first let's do this. Under the global tab, what you will see is mesh parameters. Because we have assemblies, they're going to be meshed separately. We're not going to touch the defaults for max element size or the gaps. And let's just change, let's go generate a coarse mesh. So as you notice, this kind of changed some of the little settings here, some minimum number of elements in gap, edge count elements, and maximum size ratio is increased now. So that's it. What we do is just hit the generate button. And what happens is now it's generating mesh. There was a little window that popped up on the top right corner. It showed progress. Because this is, such a small model, it really ran very fast. As you can see, Now we have number of elements around 20,000. Also, there were some messages in our log area here, and what we can see is, it generated these many hexas, etc. We do not see any warnings or errors, so that's definitely a good sign. We can then, next step I suggest is let's check our mesh. So after settings, we go to the display tab. Let's hit display mesh, and let's, we can look at some selected surfaces. So because the fan object is selected, automatically it kind of shows the surface mesh for the fan. Another type of way to look at the mesh is a cut plane, which I typically prefer. And, you can have these multiple options. One, and here, it made a plane right across the Z plane at the mid Z plane. And here, I can switch to an X plane, for example, or I can switch to a Y plane and look at, the different sets of mesh, look at some distribution. If I'm not happy with the resolution, then I can try and reduce the sizes, improve my mesh. I can look at it in different ways. I can look at different Y planes by using the slide. Next, let's go back and regenerate our mesh using the default option. So all we do is select normal, click generate, and this is going to be very quickly generate a finer level of mesh. As you can see, it's already done. It created about 6,000 elements, and let's take a look at it. So I click display mesh, and as you can see, in the plane now we have much better resolution of the mesh in the heatsink and the amplifier region. So I'm more satisfied with this mesh. And the final thing about the mesh I want to do is check the quality. Typically, with face alignment, you want to be over 5%, and this is over 50%, which is excellent. Under volume, you don't want to have any negative values, which we don't. And in skewness, anything over 2% we can, live with. So this is almost 40%. So very high quality mesh is generated for us. So we can close our mesh now, and the next step is essentially setting up our solution. So what we want to do is, let's go under project solution settings, expand it, and double click on basic settings. Let's bring this forward and talk about this a little. So here we have the number of iterations, which default is 100. We can change it as we like. Let's make it 150. Typical convergence criteria for flow is 3 orders of magnitude, and energy is about 7 orders of magnitude. In some problems, you may want to add maybe 1 or 2 more, make it more restrictive, maybe go to 4 orders of magnitude for flow. And I've even seen, with energy, people go to 10, 12 orders of magnitude. So let's hit accept, and next we want to do a problem setup. Again, we have 2 ways of doing it. We can either go fill it out this way, or the other option, maybe do a right click and use the setup wizard, which helps us guide us through the setup. What we want to do is solve for flow, velocity and pressure, and because it's a thermal problem, we want to solve for temperature. So we go to the next step. And then this is a critical question. Is the flow mainly forced convection, or do we need to care about natural convection? In this particular problem, even though we have a fan, but we also have an enclosure for our RF amplifier, which really does not have forced convection in it. So what we want to do is then select buoyancy driven option. we're going to use Bose-Ness approximation. And then we can leave the operating pressure, you know, this is your standard pressure at sea level. Because we've said buoyancy is important, of course now we want to define the gravitational acceleration and its direction, and that depends on the, you know, orientation of our system. In this particular case, gravity acts in the minus y direction. So we hit next, and we do know the flow is turbulent, so we can hit next because we do have a fan. And then this now gives us different turbulence model options. And you know, here, and they go from, you know, simplest to more advanced options. Typically, a lot of times, you know, you want to use more for, you know, swirl things are important. You want to use realizable 2 equation, or, you know, K, SST, K omega. In this particular case, we're just going to stick to the 0 equation mixing length approach. So let's hit OK. And next. And let's see. For this problem, we're going to ignore radiation impacts. Next, we're not going to include solar radiation. And here, we're going to do an only steady state problem where variables are not dependent on time. So this is a steady state problem, and we're not going to consider altitude effects. And that's it, we're done. So once we hit done, the modeling problem setup is complete, and we can go ahead with the solution. So before that, let's double click on our basic parameters. This is where you know, the wizard helped these set up, but if you wanted to change anything, you can go to basic parameters, and then, you know, you'll see the very similar options. Here you can also define your ambient conditions. This is a steady state problem, and, you know, you have some advanced options here. Sometimes, you know, maybe we want to set up a temperature limit, and I'll show an example here. If we go to model, and then if we go to power and temperature limits, it's going to bring up our objects. And here, you know, we can place a temperature limit. If we know, you know, a particular object should not pass this, you know, temperature, we can go ahead and change it. So what we will do is we'll change the default temperature limit to 60. And you know, set the temperature limit for all objects. And now we can hit accept and close it. Before going to a run, what we want to do is also track some important flow parameters or thermal parameters to make sure the solution is converged. So for this purpose, what I'm going to do is expand amplifier, maybe take you know, one of the devices, this, and drop it under the points. So what this did was create a monitoring point for device 2, which is one of our heat sources, and we're going to be looking at temperature. You know, that's what we want to track here. Another thing maybe we want to do is let's select the maximum Y, drop it. So for our outflow region, we want to double click, and here we want to maybe track both temperature and velocity, and then we can hit done. Before we go ahead with our run, what we'd like to do is, let's see, make sure, in our basic settings, we have enough number of iterations, maybe pull this up to 300. And then another thing is maybe we want to look at our parallel settings under solution settings. This is a small model which we can just use one processor to solve, or if you have more than one processors and it's a large model, you can go ahead and select like 4, and then hit accept. And let's look at advanced settings. These typically you do not use or change unless you have convergence issues. In that case, that'll be another topic. I'll not be covering that in this video. So we're ready to run now. We can run it by essentially hitting this calculator button. Before doing that, I always want to check the model. So once I click that, it will say no problems. So if there were any blatant problems, issues, we would have seen an error message. And let's click the run solution. Once I hit this button, it's going to bring up the solve window. We can provide the solution ID name. We can just call this base solution. Then, if you have add radiation, maybe you can do that, give it another name, with radiation, without radiation. If you change turbulence models, you can name it accordingly. You'll have all these different set of solutions under this one folder. And that's it. So once we're ready to go, we hit start solution button. And then as you can see in the progress window, it's preparing an input deck for the Fluent solver. As you may or may not know, Icepak uses Ansys Fluent as a solver in the background. So right now what's happening is Icepak is preparing a case file for Fluent, and then that case file will automatically be loaded into Fluent, will start to be executed. And we will be able to track the progress as iterations go along, and also we'll look at our monitors live as the solution is underway. Once the solution is complete, Fluent is going to write out solution file and then export that back into Icepak for our viewing pleasure. And as you can see, automatically we got our run information. We can see how the solution is converging. As you can see, continuity is doing really well, and it seems to be converging very fast, and in fact it already did. And if we want to make sure the solution is more converged, we can, like I said, tighten the number of residual magnitudes, have it run some more iterations. In this particular case, looks like around 110, 120 iterations, we got a converged solution. We kind of see our device temperature is still kind of changing a little. It's not fully flatlined, but so we can see the velocities has flatlined. And then next, we're going to look at the solution and do some post-processing. Okay, once we're satisfied that we have a converged solution, we can hit done. And what we'd like to do is examine the results, but that's the reason why we built this model. So, let's just start looking under the post button. This is for post-processing. We can, do many functions, and I'm going to spend some time in this tutorial and go through most of these options. Let's first take a quick look at our maximum temperatures. So I go under post, and then I select the power and temperature values option. This is going to bring up the window that we worked before, where we defined a 60 degree as our limit, and anything over 60 degrees is we want to avoid. So we want to see, and what we see is from the numerical values, where our heat source is, we're hitting the threshold. and if we click show to hot, it's going to show the high temperature surfaces. This option is very effective if you have a very large model to quickly see where the highest temperatures are. But there are definitely better ways of looking at the temperature field. So what I'm going to do is start looking into those. One option is looking at the temperatures on our existing objects. So to do that, we can go through object face node here, or the other option is click the button here. What I'm going to do is I'm going to select my heatsink, and this will select the whole heat, all of the surfaces, or I can select individual faces as well. I'll hit accept. I'd like to see contours, so I'll put a check mark here, and I'll click on parameters. We're going to look at temperature in this case, so we can look at different things like pressure, velocity, etc. And we're going to just look at the temperature and limit it to this object's temperatures. When I hit apply, we are going to see the temperature distribution only on the heatsink. And what we can easily see is also highest temperatures are very near the heat sources, the devices, so that does make sense. And another thing of notice is our fan is on this side, so there's better cooling near the fan, and as we move away from the fan, we see hotter temperatures. So this all makes sense. That's excellent. I'm going to hit apply, and done, and done. And what you'll notice is now under our tree, there's a new object under post-processing called phase 2. We can rename this any way we like, and use it in the future for whenever we're comparing different cases quickly, so you don't have to recreate this this setup. Yet another good way to look at the solution is making a section cut. Plane cuts are pretty useful, particularly in CFD when you want to see the flow field across the domain. And what I'm going to do is I'm going to select an X-plane through the center, and then we can show different things on this plane. We can look at contours, but I want to look at vectors in this particular case. So let's check vectors, hit parameters. It's very similar. We can color our vectors by velocity magnitude, or a different scalar. And let's just hit apply. So now what you will see is the vector plot is added onto the domain here. So I can go back to my post-processing and I can inactivate my contour plot. What I see is that this is a plane through which it hits the inner enclosure. So what I will do is I'll go back to my cut, and I can, using the slider, I can move my plane, X-plane up or down. And let's, when I hit update, now this is a plane that shows the flow through our heatsink. So now, we kind of see the blockage of the heatsink. Also, the strong fan flow. You can see, right in the center, there is good cooling, and how the flow leaves the domain. So we can do update and done. And let's inactivate this as well. And as a reminder, when you inactivate it, you see it vanished under post-processing. It goes under the inactive folder, which is right here. And then here, again, we can reactivate, these objects. So next thing is, the third button here is the ISO surface. So maybe I want to capture the high temperature regions. So I'm going to click on ISO surface, create a new ISO surface table. And then maybe I want to look at values 55 degrees C, which is on the higher end to catch the high temperatures. And then let's hit show contours, let's hit display, and as you can see, quickly displays us the high temperature isosurfaces. And then all right, we can hit done, and then we can also hide this. The next step, what we'd like to see is from the report tab, we want to look at a summary report. So this will bring up a new window for us. Here we can get numerical values for different objects. And I'm going to show a couple of examples. What I'm going to do is I'm going to click new, and I'm going to select my object. Let's again, start with our heatsink, hit accept, and then let's say I want to see on all sides. I can look at temperature, which we visually did. This time, maybe I'm interested in the heat flow. Another, one I could add, for example, is what is the flow rate of the fan, right? We're using a fan curve, not specifying the mass flow rate. So I'm going to select my fan, and then I'm going to inquire about the volume flow rate. Another good one is I can add a new one and look at some properties on a face that we defined before, such as the phase 2. So we can go under our list, we can go under post-processing, pick phase 2, and then maybe look at the temperature there. So once we made our selections, we're gonna click right, and then it's going to pop up a new screen, a new panel with the answers. So for our heat sink, it's going to give us our heat flow in watts, and then we get our volumetric flow in meters cubed per second, and then in degrees C, we're going to see min-max standard deviation of the temperature for the phase 2 object. So we can hit done, and then we can hit close now that we've extracted the information we needed. Let's orient to, let's see, positive Z direction. Okay, and I will talk about the variation plot in the bar here. So I'm going to go ahead, click on this, and it's going to essentially create an XY type plot as we define it. So this time I want to look at Y velocity, and then I'm going to select the from screen, and then I'm going to click on the center of the heatsink, and then I will say create. So what this will do is, at that point, it essentially made a section cut, and it's looking at the Y component of velocity. So we're the x-axis in our plot is the distance in the Z direction. So if I flip it over, so now this direction is our X plot, and as you can see, we have some velocities, and where the fins are, the velocity has to go down to 0. This kind of very quickly shows how the velocity is distributed between different channels of the heatsink. Looking at this, maybe you want to add another fan. What you're seeing is, lower flow velocities toward the edges, and that's to be expected because when you look at the domain, the fan does not cover the whole width of the heatsink. So this essentially wraps up our presentation for our model, and I'd like to thank you for your attention. Have a great day.